Hello, we're going to have a look at two lossless algorithms in this video, and let's just start by briefly going over lossy versus lossless again, because it is relevant for understanding how the lossless algorithms work. So lossy, we've got some original data, we apply the lossy algorithm to compress it, and we end up with the original, but with some data being deleted. Now that file, I can double click, I can open it, I can view it. It will be a smaller file size, but the quality will be a little bit reduced. And we use lossy with images and sound and videos. We don't use it with text. Lossless can be used with all of those, but also text and program code as well. So lossless is a tiny bit different. We still apply a lossless algorithm. We'll look at two in this video, and we end up with not data being deleted, but it being stored in a more compact, more efficient way. The key thing to realize is that lossy, once it's in this compressed format, I can open it and view it. I can't ever go back to my original. So the original is gone at that point. The compressed version is what I use on my computer. But lossless, I need to decompress it to be able to view the original again. Lossless has no loss in quality. So really this compressed version should look exactly the same as the original. Well, how does it do that? Well, it has to basically undo the process which put it in the compressed format in the first place. RLE is the first of the two lossless algorithms we'll look at now. RLE stands for run length encoding. And this works on the principle that consecutive data being repeatedly stored is redundant. Redundant means I don't need to store it. And in this context, it means I'm wasting storage space by storing it. So the word run in this context is a sequence of consecutive values. So if I've got the same value being repeated multiple times, that is a run. And what RLE will do to try and represent it in a more compact way is represent the data using frequency value pairs. Well, what does this mean? Well, let's just take an image. We can apply RLE to images. Images can be quite effective with RLE, especially if I've got blocks of the same color, ideally. So the sky here in this image is just a block of blue, albeit different shades of blue. So if we could look up really, really close at the pixels in just say this region, we might, to simplify a bit, have two shades of blue being represented here. What I've put in these boxes, the boxes representing what should be square pixels, are the hexadecimal color codes for those colors. So we can see we've got, if you can't see visually, we've got this color code here, which is repeated at the start and also at the end here 3 times. We also have another shade of blue, a little bit lighter, which is 3 in a row over here. So these are runs. This first pixel on its own isn't a run, but I've got a run of 3 here and a run of another 3 here. These are consecutive values in my file. And the principle is storing these separately is just a waste, because what I can do is I can compress it into RLE and instead replace these repeated values with frequency value pairs. So this is one way we could represent it. I've put brackets around each pair and I've separated these with commas. The first value in this pair is our frequency. It's how many times the value appears. Well, this first pixel only appears once in a row. So I put a 1, then I put its value, which would be in binary. In reality, I'm showing this in hexadecimal just to simplify. The next pair, we can see I've got 3 in a row of this 75B9E7 code. That's why I put 3, comma, its hex value. And again, I've got a run of 3 at the end here. So I do 3, comma, this other color code. So instead of storing these codes 3 times, we are storing it once alongside how many times it appears. And remember, we have to decompress. So this will be stored in a more compact way. But when I double click it to open it, we'll need to reverse my process to restore it. Well, given just this RLE, I'd be able to restore the original file with no issue at all. No information is being lost here. I've got 1 lot of this first one. I've got 3 lots of this second one. And I've got another 3 lots of this first one again. So I could restore it with no loss of quality because it is reversible. Here is a possible exam question, a beautiful exam question, because it should be quite easy to do. We need to apply RLE to this sequence of characters here. So it's not pixels anymore, it is characters, so text. Well, one other way we could represent it is like this. First of all, I've got 3 lots of A. So I could do 3, comma, A like that. But I also might want to do shorthand and just go 3A. I've got 1B. Despite that B still being on its own, I still need to write it down. 1B. I then got 1 A. I've then got 2 Bs. I've then got 2 Cs. Then I've got 1 A. That's a slightly more compact way of writing it, which you will often see in mark schemes. The commas and the brackets can be helpful if you've got slightly awkward data like the hexadecimal I just showed you. If it's quite simple data, just doing it literally frequency value can be a bit more compact. Now, a mistake people make sometimes is they will go, oh, I've got 3, 4, 5 A's in this, therefore I can go 5A. Oh, I've got 3 B's in this, therefore I can go 3B, and so on. That is not how we do it. The reason why we can't do this is because how would you restore it? How would you decompress it and put it back to the original? You wouldn't be able to, because you wouldn't know where these A's came from, in what order were these A's in. We need to fully write it out in the same order so that we can decompress it and put it back to the original. Now, you can see actually my correct answer in the box here has turned out to be longer than my original, which proves that actually RLE doesn't always improve file size. If you've not got many runs, if you've not got many repeats consecutively, it will not improve file size. Here, I've only got relatively short runs, and I've got a couple of characters on their own. For the characters on their own, there is no benefit because I have to store the frequency alongside the value, so it's doubling the size effectively, which is not helpful. A second type of lossless compression is dictionary coding. This is really a category of lossless compression. There are lots of specific algorithms within this category, lots of which are quite complicated and they can be quite different actually. Let me give you a high-level summary of the approach because that's what you need for A-level. So dictionary coding works on the principle that groups of values can be substituted with shorter binary codes. And this is particularly beneficial if these groups of values are repeated throughout your file. RLE works very much on single values, just repeated consecutively. Dictionary coding works on groups of values which are dotted about your file, potentially. So to give you an example, this one here is not a perfect example because it's so short and isn't as dotted about as it could be. It's hard to show a good example which can fit onto a slide because it works best if it's quite a big file, but this is just an example of how this works. I've got some text here. We can apply dictionary coding to text, but also images and sound and things like this, and program files. So I've got some text here though. How would I go about compressing this? Well, different algorithms within this category will work differently. There are more optimal ways to do it and different ways of going about it. What I did here was just go through this text and look for what is repeated. And if it's not repeated, what is the kind of longest block I can create and assign a short binary code. Because let's not forget with text, with every character here, I need to store it with ASCII using 8 bits, for example. So what can I try and shorten here? Well, my attempt is this. This is my dictionary. So the dictionary is a data structure which has essentially a lookup. So we're looking up or substituting what you might call a token with a shorter binary code. A token is our group of values. So the first token I've got is row. I've given it a binary code. We then have got a comma, another binary code. Spaces have to get included. That's given another binary code. Spaces appear throughout this entire bit of text. So that having a short binary code is beneficial. A space in ASCII is 8 bits, but I've shortened it to 4 bits here. So that's great. Unfortunately, I've got rows 3 times here, but 2 of these rows are lowercase. That means it's got to have a different code to the uppercase one. Then I've got something like your boat, where this is only showing up once. So I'm going to combine it as a single group. It doesn't just have to be a single word to give it, again, a short binary code. And my approach goes on like this. So the example here is not the best because ultimately, like merrily, I've got 3 times in lowercase. I could have grouped this as one big group, but I'm imagining merrily might appear somewhere else in my text file. So therefore, I'm kind of keeping it separate. But what I can do is to actually compress it. Once I've done this first step, which is populating my dictionary, I can just substitute each token with its corresponding binary code. So row is my first word. This is 4 zeros. Then got a comma. This is 001. Then 0010 is a space, and so on and so on. So we can see how easily it is to decompress, to undo my process. Because to undo the process, as long as I have my dictionary still, I can just substitute back again. So 4 zeros is row, 001 is a comma, 0010 is a space. I can easily decompress to go back to my original. So again, like RLE, no information is being lost in this process. And even with this slightly flawed example, if we were using 8-bit ASCII, This original is 107 bytes, and the compressed version is just over 11 bytes. Although the big caveat is we always have to store the dictionary alongside the original. Without the dictionary, this becomes complete nonsense because I'm unable to decompress it back to the original. So the dictionary takes up space. That might mean actually when you include the dictionary, it takes it above 107 bytes, but it depends on how you're storing this dictionary.